Hello everyone. In this video we are going to talk about core-periphery structure in social networks. Core-periphery structure has nowadays become one of the most important and most talked about structure in the field of social network analysis. It comes in the category of mesoscale structures. Till now, community structure was the one which has gained the attention of scientists over years. But now core-periphery structure is a kind of giving equal competition and is attracting equal attention from the side of researchers. So in this talk we will try to understand what exactly is a core-periphery structure and how do we determine its existence in a real world network. So how many of you know about the Milgram experiment? Milgram experiment is again a very well known experiment. It was conducted by social psychologist Stanley Milgram to understand how small our world is. The experiment was very simple. Milgram have chosen some people from the random parts of the world. Like you can choose a person from a village in South Africa, from some city of USA and so on. They were the you can say they were the applicants or they were the participants for his experiment, and all of these participants they were asked to forward a letter to a target person in Boston. The letter consisted of name, address and some of the personal information of this target person. But while forwarding the letter to the target persons, there were some rules of the game that needed to be followed, and the rule of the game was you cannot directly post this letter to the target person. What you can do, you can give this letter to one of your friends whom you know on a first name basis. Please notice, only to the friends whom you know on a first name basis. So what do you mean by first name basis here? It means that your friend should be so close to you that you are able to call him by his first name. So it basically means you can give these letters only to your very good friends and then ask them to forward this letter to their friends and so on. And then Milgram, he tried to see in how many number of steps does this letter reach to the target person. Then all of us would think that this number would have been very large, but to our surprise the results of the Milgram experiment demonstrate that the median of this number was 6. That is, all of these letters they have reached to the target person in a maximum of 6 steps. Now although Milgram experiment is one of the most important work in the field of social network analysis, but there were various critics of the experiment after it was conducted. And one of the most important critic and one of the most important point was it was seen that Milgram experiment turned out to be highly successful when your target person is a high status people, like say a college professor or a journalist. So it's like if I give you a letter and I ask you to forward it to some random person, say John, and see another example in which I give you a letter and ask it to somehow make it reach to Obama. Then in the Milgram experiment it was seen that the second thing was more likely to get successful as the first one. So this particular critique of the Milgram experiment gave rise to a very nice observation, and the observation rises from the question, is there a hierarchy in the world? Why is it easier to reach Obama but it is difficult to reach some other person like John in the previous slide? It happens because there is a hierarchy in the world. The people in our world are not equal. There are some high status people in the world who have a lot of resources, who can travel to different parts of the world, who can be a part of different clubs, and these people they communicate with each other. These high status people, they are very good friends with each other. So you can see in this figure as it is shown, here is one person who is running with all the money and all the resources, and most of the people, majority of the people, they generally lie in the category of low status. So this has been depicted by this diagram in the book Networks, Crowds and Markets by Kleinberg. So it shows that our network is organized in such a way where the high status people, they form the core of the network, which is densely connected and which have access to all the different parts of the network, whereas the periphery nodes, they are atomized around the boundary of this core. And we can also see, once we remove the core from the network, it becomes impossible for these periphery nodes to contact each other. So it's very easy to reach one core node from another core node, to reach a periphery node from a core node, to reach a core node from a periphery node, but it becomes difficult to reach from one periphery node to another periphery node. So this was just a brief idea given by Kleinberg in his book. But the formal study for what a core periphery structure has started in around 2000 with a paper published by Stephen Borgatti and Avret with the name Models of Core Periphery Structure. So let us try to study that paper in little bit of detail. So the question there was, okay, we agree that there is a core in a network, but can you give an algorithm for how do I detect a core in the network? So suppose it is a network that I show you in this figure. So can you give me an algorithm what is the core of this network, though there doesn't seem any well-defined core in this network? Okay. So for giving an algorithm for this, they propose something which is called a perfect core periphery structure. So first of all, let's understand how do you make a perfect core periphery structure and what is its meaning. According to a perfect core periphery structure, all the nodes in core, they are connected to each other. So as you see in this figure, 1 and 3 are core, so these will be connected to each other. If there were more nodes here, all of these core nodes will form a clique among themselves. Then all the core nodes, they will also link to every other periphery nodes. So in this figure, 2, 5 and 4 are the periphery nodes, and you can see that 1 and 3 are connected to these periphery nodes, to all of these 3 periphery nodes, but no 2 periphery nodes will be connected to each other. So this kind of a structure is called a perfect core periphery structure, where there are connections between every 2 core nodes and every set of a core node, every pair of a core node and a periphery node, but no connections between 2 periphery nodes. The next thing is, every perfect core periphery structure can be defined by a sequence. And how do you define the sequence? You assign a binary value with every node. This binary value is 0 if your node is a periphery node, and it is 1 if the node is a core node. So can you identify the correct sequence for this structure? Here we know that node number 1 and 3 are core nodes and rest all are the periphery nodes. So sequence number 2 corresponds to this structure, where 1 is your core node, 2 is your periphery node, 3 is again your core node, and 4 and 5 are your periphery nodes. So we can clearly see here that every perfect core periphery structure can be represented with the help of a sequence, and the length of this sequence will be equal to the number of nodes in that structure, in that graph. Okay, so now this network was given to us, and we want to determine the core nodes in this network, which are the core nodes and which are the periphery nodes. The way that Stephen and Borgatti used to identify the core is very simple. Now here is a network with 5 nodes. Out of these 5 nodes, how many sequences of perfect core periphery structure are possible? That is, you forget this graph. I give you a graph on 5 nodes. I just give you 5 nodes. Say I do not give you the edges, I just give you the 5 nodes. So how many perfect core periphery structures can you make out of these 5 nodes? It will be equal to the number of sequences possible. So corresponding to every sequence, you can lay down the edges and make a perfect core periphery structure. It means that corresponding to n number of nodes, there are 2 raised to the power n number of perfect core periphery structure possible. So now if I forget the edges of this network corresponding to these 5 nodes, I can write down here 2 raised to the power 5 sequences. Each sequence will represent some perfect core periphery structure, and then I will try to see which of these structure matches the most with this graph. And the structure which matches the most with this graph, I will give the corresponding assignments of core and periphery to this graph. But it will be very difficult for me because here the number of nodes is 5 and there will be 2 raised to the power 5, that is 32 sequences. So you will have to compare each and every sequence or each and every structure, perfect core periphery structure corresponding to a sequence with this graph, which will be very difficult. And if you raise the value of n, it will rise exponentially. So it is very difficult to compare each and every sequence. So we need some nice algorithm for finding out the best sequence which matches this graph. So let us see how can we do it with the help of genetic algorithm. So again, genetic algorithm is an algorithm which is generally used in artificial intelligence to converge to a solution which is quite close to the optimal. So we know that it is not possible for me to compare my given graph with each and every sequence. So what do? I take some sequences out of the possible sequences. So like if there are 32 sequences, maybe I just pick 4 of them. So that makes my initial population. So initial population, it consists of 2k perfect core periphery structures or 2k number of sequences. Now I can find a fitness function for each of these sequence. And what is my fitness function here? Fitness function is the similarity between the given perfect core periphery structure that is defined by the particular sequence or a particular member with the given graph. So that defines my fitness function. According to this fitness function, I select some of the members from here. I do a crossover operation. We'll see what is a crossover operation. I do a mutation operation. After performing both of these operations, I get a totally new population, and I repeat the same process, and I will stop at a moment where my fitness function will give me a very good value. Let us see how to do that. So say it is my initial population. Out of the 32 possible sequences, I select 4 of these sequences to be my part of initial population. After this, I need to find a fitness function. So I calculate the fitness function based on how much similar a perfect core periphery structure determined by these sequences with my given graph. That can be easily done by comparing the adjacency matrix of both the graphs. So let's say we calculate the fitness function for all of this population, and it turns out to be these values. According to the value of this fitness function, I select some of the members for reproduction. So since the value of this particular member is 44%, I select it. Then I select the member with the value 34% of fitness function. Then with a high probability, I again select the same member with a value of 44%, and then one with the 18%. So you can see in this case, the member which was having the least fitness, 4%, it is discarded and it is not considered for reproduction. So I write down the 4 selected. Okay, so I write down 4 of these selected members here, where you can see one of these is repeated, which is corresponding to the member which was having a 44% fitness. So this is my selected population. Now I need to apply a crossover operation on this selected population. By crossover means we are going to merge these values, we are going to merge this population with each other to form a new set. How do we do that? So we select some positions for crossover. So let's say I select a position here for both of these members and a position here for both of these members. After crossover, what I am going to do, I'll flip this particular portion with this particular portion. So I'll flip both of these portions for these two members, and I'll flip both of these portions for these two networks, for these two members. So you can see that once we do it, we get a new population. So you can see that 100 and 010, they get replaced with each other, and similarly here 10 and 01, they get replaced with each other. So in this way I get a new population which may have a higher fitness value as compared to before, but still one operation is left, that was mutation. Mutation is a very simple operation. Mutation simply asks me to flip one bit randomly for every member. So I flip one bit randomly for every member, and now this is my final new population, and I can apply a fitness function on this population to see whether I get a high fitness function. So maybe if one of these members it matches around 80% with my given graph, so my solution is obtained. Otherwise I'll keep repeating this genetic algorithm again. So rest of this lecture will be taken forward by Debarati Das. So thank you.